Since the dawn of human history, we have looked up at the night sky with wonder and curiosity. The stars, the moon, and the sun were not just lights in the sky. They were mysteries that inspired our imagination. Ancient civilizations created powerful stories and myths to make sense of the universe. They imagined gods painting the sky, celestial creatures battling in the heavens, and giant animals chasing the sun across the sky. These stories were passed down from generation to generation, marking humanity's first attempt to understand the vast and seemingly random world around us. Myths gave us a sense of order, structure, and our place in the cosmic drama, setting the stage for our first steps toward exploring the universe. As societies developed, our methods of inquiry also evolved. The ancient Greeks were the first to move beyond mythical explanations and adopt a systematic and philosophical approach. They began to use logic, reason, and observation to understand nature. Thinkers like Thales, Anaximander, and Pythagoras introduced the idea that the universe operates according to natural laws, not just the will of the gods. They proposed that everything is made from basic elements like water, air, or even numbers. This was a revolutionary change in human thinking, a pivotal moment when we began to ask why and how in a systematic way, seeking answers not just in stories, but in the very fabric of reality. Among these great Greek thinkers, Aristotle stood out as a prominent figure, whose ideas dominated Western thought for nearly 2,000 years. He proposed the geocentric model of the universe, with a round and motionless Earth at the center of everything. Around our planet, he imagined transparent and perfect circles, celestial spheres carrying the sun, moon, known planets, and finally the distant stars. According to Aristotle, the sky was a perfect and unchanging realm made of a fifth element called ether, while the earth was a place of change and decay. His comprehensive and logical system offered a complete picture of the universe, beautiful and satisfying. Aristotle's cosmological theory was powerful because it was based on observation and logical reasoning, matching what people could actually see with their own eyes. The sun appeared to move around the earth, and the ground beneath us felt completely stable. His philosophical framework became the foundation of astronomy and scientific thinking for centuries, shaping the intellectual world of both Europe and the Islamic world. It was a major step, a detailed map of the universe. Even though it was later proven wrong, it was humanity's most refined attempt to understand our place among the stars. The journey from myth to a rational, though imperfect model is a powerful testament to our thirst for knowledge. The period from the 9th to the 11th century, often called the Islamic Golden Age, was a remarkable chapter in the history of science. While Europe was passing through the Dark Ages, cities like Baghdad, Cairo, and Cordoba were centers of astonishing scientific progress led by scholars. These scholars translated the works of ancient Greeks, such as Aristotle and Ptolemy, preserving this invaluable knowledge for future generations. But they did not merely preserve knowledge, they expanded it through research and innovation. Astronomers like Al-Battani refined calculations of the length of the year, while Ibn al-Haytham played a foundational role in the science of optics, which later proved crucial for the invention of the telescope. This era served as a dynamic bridge, connecting ancient wisdom to future scientific discoveries and igniting a spirit of inquiry that would spread across the world. Centuries later, the Renaissance began in Europe, a revolutionary scientific era from the 15th to the 18th century that completely transformed our understanding of the universe. This scientific revolution was sparked by courageous thinkers who dared to challenge the old ideas of Aristotle. Nicholas Copernicus, a Polish astronomer, introduced a revolutionary idea, the heliocentric model, placing the sun, not the earth, at the center of the solar system. This was a profound shift, challenging not only scientific theories but also religious and philosophical beliefs. Copernicus's work, published just before his death, laid the foundation for a new era of cosmic discovery and intellectual freedom. After Copernicus, a wave of brilliant scientists shattered the old worldview. Johannes Kepler, using careful observational data, discovered that planets move in elliptical orbits, not perfect circles as Aristotle and Copernicus had believed. Then came Galileo Galilei, who turned a newly invented instrument, the telescope, toward the heavens. What he saw was revolutionary. Mountains on the moon, moons orbiting Jupiter, and the phases of Venus. These observations provided direct and powerful evidence that the old geocentric model was incorrect. Galileo's bold support for the Copernican system brought him into conflict with the Church, but his work transformed astronomy from a philosophical debate into an observational science. This scientific revolution reached its culmination with Sir Isaac Newton. In his monumental book, Principia Mathematica, Newton described the laws of motion and the law of universal gravitation. He showed that the same force that causes an apple to fall from a tree also keeps the moon in orbit around the Earth and the planets around the sun. Suddenly, the heavens and the Earth were united under the same universal mathematical laws. The universe was no longer a mysterious divine realm, but a grand, predictable machine, a celestial clock that could be understood through reason and mathematics. Newton's synthesis was a triumph of human intellect, providing a powerful framework for physics that dominated for more than 2 centuries. Newton's beautiful, clockwork-like universe presented a complete and simple picture. But as the 19th century entered the 20th, new mysteries began to emerge that classical theory could not explain. The stage was set for a new scientific revolution, led by a young Albert Einstein, who was working as a patent clerk. In 1905, Einstein published his special theory of relativity, which completely transformed our understanding of space and time. He proposed that the speed of light remains constant for every observer, and that space and time are not separate and absolute, but are intertwined in a continuum we call space-time. This theory led to astonishing phenomena such as time dilation and length contraction, meaning that our everyday experience of reality is actually just a small part of a very strange and magnificent universe. 10 years later, Einstein expanded these ideas with his masterpiece, the general theory of relativity. This was not just a theory of motion, but a completely new theory of gravity. Newton had described gravity as a mysterious force acting at a distance, but Einstein explained gravity in a completely different way. He said that massive objects, like stars and planets, do not pull each other with a force, but instead bend or curve the fabric of space-time around them. Smaller objects then follow these curves, just like a marble rolling on a stretched rubber sheet with a heavy ball placed at its center. General relativity presented a dynamic picture of the universe, where space and time participate in a cosmic dance, and this theory was later confirmed by countless experiments. Meanwhile, as Einstein was unraveling gravity on the largest scales of the universe, another group of scientists was exploring the microscopic world, giving birth to quantum mechanics. Quantum mechanics describes the laws that govern atoms and the universe at the level of subatomic particles. It revealed a reality that is fundamentally uncertain and probabilistic, where particles can exist in multiple places at the same time, and energy does not come in a continuous flow, but in discrete packets called quanta. Scientists like Max Planck, Niels Bohr, and Werner Heisenberg showed that in the subatomic domain, principles operate that challenge common sense. Newton's predictable and definite universe was replaced by a world based on chance and probability, where at the most fundamental level, there is a blurry and chaotic world. At the dawn of the 20th century, the emergence of general relativity and quantum mechanics created a deep divide in physics. General relativity beautifully describes galaxies, stars, and the universe on large scales through gravity, while quantum mechanics explains particles and the microscopic world of forces. But these two pillars of modern physics are fundamentally incompatible. They speak different mathematical languages, and their principles often conflict with each other. The quest to unite them into a single universal theory is the greatest challenge in physics today. This grand quest is an attempt to understand all the fundamental laws of reality, from the smallest particle to the entire universe. Our modern understanding has been encapsulated in a standard model of the universe, which is often called the Lambda CDM model. This model is our best scientific story about the cosmos, and it is supported by a vast amount of observational evidence. It tells us that the universe began about 13.8 billion years ago in an unimaginably hot and dense state, which we call the Big Bang. Since then, the universe has been continuously expanding and cooling, paving the way for the formation of galaxies, stars, and planets. The lambda in the model's name represents dark energy, a mysterious force that is accelerating the expansion of the universe, while CDM stands for cold dark matter, a hidden form of matter that provides extra gravity to hold galaxies together. This model has achieved remarkable success in explaining a wide range of cosmic observations, but the standard model is still incomplete. It presents us with deep challenges and profound mysteries. According to this model, two major components of the universe, dark energy and dark matter, remain completely mysterious to us. Altogether, it is believed that these two make up about 95% of the entire universe, yet we still do not know what they actually are. Ordinary matter, stars, planets, and ourselves, makes up only 5%. We are like explorers who have mapped a vast continent, but can only see a few small islands along its shore, while everything else remains hidden in deep, uncharted mist. This incredible journey of cosmic discovery would not have been possible without the continuous evolution of telescopes. From Galileo's simple spyglass to the Hubble Space Telescope, and now the James Webb Space Telescope, our eyes on the universe have become more powerful than ever before. These technological marvels allow us to look further back in time, revealing the birth of the first galaxies, and making it possible to analyze the atmospheres of distant planets. Each new generation of telescopes opens a new window onto the universe, revealing details we never even imagined, and often giving us even more puzzling questions. They are our time machines and our cosmic guides, constantly pushing the boundaries of our knowledge and fueling our endless curiosity. Our quest to understand the universe is a journey that began with ancient myths and has brought us to the very edge of modern science. From Aristotle's geocentric universe to Newton's clockwork cosmos and to Einstein's curved space-time, our perspective has expanded beyond measure. Today, we stand at a remarkable point in this journey, equipped with powerful theories and incredible instruments. Yet, despite all we have learned, the universe still keeps its deepest mysteries. The existence of dark matter and dark energy reminds us that we have only just begun to scratch the surface. The story of cosmology is the story of humanity's boundless quest for knowledge, a beautiful and ongoing adventure into the heart of the great unknown.